a very good evening to the external panel, all lecturers and fellow students. My name is Uyi Kang from Electronic Engineering, and today I would like to present my FYP poster with the title of AI Integrated Sun Tracking Algorithm. So without further ado, please allow me to start my presentation. And here's the list of content that I will discuss, including the project overview that provides abstract discussion, problem statement associated with the investigation of the study and describe the research objective. Next, the methodology will discuss the mathematical derivation of spinning elevation sun tracking formulas that will be integrated into Python coding. And besides, AI sun tracking algorithm will be implemented using deep neural network is also included. Furthermore, the simulation results are presented and discussed. And finally, the presentation ends with conclusion. First, I'll be explaining on the problem statements for a better flow of the presentation. So nowadays, the energy demands keep on rising due to the increased population in the world and technology developments. Therefore, it is essential to find an alternative source of energy to provide more sustainable energy. Solar energy, the most abundant energy source on Earth, is an excellent alternative source in this case. And with more and more advancement in technology, it has a very large potential in supplying energy for the whole world for a virtually infinite period. In this research, concentrating solar power technology will be focused on integrating the sun tracking algorithm, also known as the central power system. The central power system actually consists of a central receiver tower located at the very middle of the field, and there will be thousands of heliostates, also known as mirrors, surrounding the central receiver tower. Thousands of the mirror that is aligned properly will reflect and focus the sun ray to the central receiver tower. Inside the receiver, the absorbed solar radiation will be turned into thermal energy to produce electricity. And this technology is beneficial where it can achieve a very high solar conversion efficiency and has tremendous potential in replacing non-renewable energy in the future. However, the heliostat requires a complex sun tracking algorithm. The spinning elevation sun tracking algorithm can be used to implement the tracking algorithm with the knowledge of the trajectory of the sun in the sky, structure of the heliostat, and central receiver tower. And after the spinning elevation method has been implemented, the performance and accuracy of the solar tracking system can be further improved using artificial intelligence sun tracking algorithm integrated into Jetson Nano platform to precisely align the heliostat in the field from time to time to obtain maximum energy output for the solar system. The sun's tracking system ensures that the heliostat's optical axis provided by the camera view plane is constantly aligned between the midpoint formed between the solar vector and target vector. So how do we identify the solar and the target? And this algorithm will be using image recognition to identify the solar object and target object in the image captured by a camera. The approach is accomplished using object detection to identify the sun position and target position based on neural network, which is the model to perform object detection. So it's like how we, as a human, identify an object as an apple, orange, or other stuff. And in this approach, we will train the machine to identify the sun and target. The model is run with TensorRT in the Jetson Nano platform for handling the trajectory motion of the sun and achieve robust detection for the sun and central receiver tower. In a brief explanation, this research is about the AI sun tracking algorithm for central receiver tower-based heliostat, where the light ray from the sun is shined on the heliostat, and the heliostat will reflect the ray to the central receiver tower. So our main purpose is to adjust the heliostat position automatically based on AI, such that it has a base configuration to reflect maximum of sunlight. The final simulation results are promising since the trained SSD MobileNet V2 identifies the sun and target precisely with real-time inferencing performance. With the identified object, the heliostat can align to the desired aiming point implemented using the AI sun tracking algorithm. The objectives for my final year project are first to implement a spinning elevation sun tracking algorithm for the heliostats. Different position vector and angles are being studied here to derive the tracking algorithm. Next is to study a neural network model for object detection, and different models will be evaluated to perform transfer learning. And the final objective is to integrate AI in sun tracking algorithm and evaluate with Jetson Nano AI board. There will be two sun tracking methods being implemented in this heliostat for the central object sun and target without the ability to perform solar tracking algorithm. Therefore, the AI sun tracking algorithm will be implemented as shown in Figure 5 to provide real-time solar tracking by monitoring and adjusting the heliostat position. The trained model and sun tracking algorithm are combined and integrated into a Python script to allow the AI sun tracking algorithm to perform efficiently and precisely. The program will be first loaded with the custom SSD mobile net detection network model for object detection, sun and target, and after that, the program will capture and process video frames from the camera until it detects the sun and target. By extracting the information regarding the central pixel for sun and target, the midpoint between them can be calculated, and if there is any deviation from the desired aiming point, signal will be sent out to adjust the heliostat position until the heliostat is aligned correctly. Next, moving on to the result and discussion. For the spinning elevation angle, simulation results show that the sun position and heliostat angle can be calculated according to a different location, time, and heliostat layout. And for the AI sun tracking algorithm, the trained deep learning model MobileNet V2 is evaluated using performance visualization based on loss vs 100 epochs. Different data set of 50 images and 100 is used as a manipulate variable as well as the batch size, where batch size of 1, 2, and 4 is used. The analysis of the learning curves shows that the trained model has a good learning rate, and by increasing the number of data sets and batch size, the neural network model has a better optimization in the internal parameters, where better model performance can be built in predicting data. The model with the lowest loss of 0.3716 trained with 100 data and batch size equal to 4 is used to run the AI sun tracking algorithm. And figure 7 shows the output stream, which is recorded from the video capture on Jetson Nanoboard to evaluate the functionality of the AI sun tracking system. The model is able to identify both object, sun, and target in the image plane captured by the camera. And once both objects has been identified, the AI system will start performing sun tracking algorithm. The midpoint between the sun and target is calculated and displayed as the purple dot with the coordinates specified. And this is the desired aiming point. If there is any deviation between the camera alignment and the desired aiming point, signal will be sent to the heliostat to adjust the position. After adjust the position, the camera will be aligned to the desired aiming point as shown in figure 7. In conclusion, the spinning elevation sun tracking algorithm for heliostat base has been implemented in detail by understanding the trajectory of the sun in the sky. In addition, an AI sun tracking system has been developed into an embedded device known as Jetson Nano Developer Kit B01. This approach is done using object detection based on a deep neural network. After evaluating different neural network models, SSD MobileNet V2 is chosen as the base model to perform artificial intelligence due to the fast, lightweight features and ability to implement in an embedded system with real-time performance. The trained model has a minimum loss of 0.3716 and the best accuracy object detection, trained using 100 data sets and batch time equal to 4. And the neural network model is successfully implemented and evaluated with the Jetson Nano board. That's all for my presentation, and thank you very much.
Okay, thank you, students. Hi, Alo, Dr. Mark, and Tia Sharo. Any question for the student?
Sorry, Aaron, you first.
Sorry. Student was
Yeah, correct.
Do you think this method will be used widely by the private sector? What do you think of your idea? Do you think it's
I think
public
still need I think still need some further research on the AI sun tracking, because this one is based on just one helio, different light and viewpoint, and sometimes the camera is not able to detect if I just identify the pixel within it. And if I use AI to train the model with a lot of image data sets, and even though there is some slight changes, is in the viewpoint, and there's and the model able to detect for the sun also.
Your image data set is lots of pictures of the sun at different positions, and you also have the sun coordinates at those positions, is it?
Yeah, correct.
Where do you get this information?
This one I self-capture on myself. I create the data set on myself. So manually use the camera to capture and draw the bounding box over the sun.
Okay. And how about the sun position? So I can understand when you take a picture of the sun, how do you triangulate that with the sun location?
So when I take the picture, I just draw a bounding box over the sun. Yeah, then that is the position of the sun.
What is the position? Is it do you have
camera.
the do you have the pan tilt and so
Sorry,
the idea is you're able to position the heliostat, right?
Yeah, correct.
So you have what, the 3D
The
coordinates of the
heliostat
sun, or?
no, it's just like a 2D image. The heliostat is facing the sun and then the central receiver tower. Then it will calculate based on the both object midpoint and then align correctly. Yeah.
Okay, all right. No further questions. Thank you.
Okay.
All right. Hi.
Hi.
Good afternoon. So basically, your research topic reminds me of my FYP projects, whereby I did kind of like the same thing, but I compute heat gain from solar. So and I personally like this research topic, because you know that the mega trend nowadays, like what Dr. Mark mentioned, was that it is the industrial revolution 4.0, and also the sustainability. And in Europe, so they basically have agreed to achieve carbon neutral by 2050. And uh, I work for a German company, and our company is already basically uh, sell out few products involving industry revolution 4.0. So I think you integrate both sustainability and IR 4.0, and I think this is really good. So I have few questions basically. And by the way, about the calculation, do you also refer to ASHRAE handbook, or which source of literature did you refer to in terms of the calculations and all that?
I refer to the previous senior study in University Tunku Abdul Rahman also. Yeah, she also doing the spinning elevation and Azimuth elevation algorithm. Yeah, so
Okay.
basically this is the main.
All right. So maybe I can suggest you to also look for ASHRAE handbook. It is spelled as ASHRAE, Association of Heating, Refrigeration, and Air Conditioning Engineer. So they provide this step-by-step calculation about the azimuths and all that. All right.
Yeah,
And then
sure.
yep, my question will basically, what is your next step? I mean, you have come up with the algorithm. So are you planning to turn it to a real prototype, whereby you can measure the energy efficiency gain with and without the AI?
Yeah.
So what do you think the next step of this research?
Yeah, actually original I'm planning to implement this, but due to the current situation MCO, so it's quite, yeah. So in future, maybe there will be some photovoltaic panel to measure the energy and evaluate more on this algorithm, so to make sure that it can function properly. Yeah.
All right, that's all. Thank you.
Okay, thank you.